Hello friends, myself Dr. Nandakumar Raubale from College of Engineering Ambajogai is going to deal with Applied Thermodynamics 1. This is our 25th lecture. In previous lecture we have discussed the numerical on modified Rankine vapor power cycle. So in today's lecture we will discuss numerical on reheat vapor power cycle. Let us see how to solve a problem on a reheat vapor power cycle using steam table and Mollier chart both. Let us see here a problem. The steam at 90 bar and 480 degrees Celsius. So steam enters at pressure P1 is equal to 90 bar into the turbine, and temperature of steam is 480 degrees Celsius, means this is temperature of superheated steam T sup 1. Temperature of steam at the inlet is 480 degrees Celsius in degrees Celsius is supplied to steam turbine. The steam is reheated to its original temperature. What is original temperature? Again 480 degrees Celsius. First steam is expanded and then afterwards it is reheated to again temperature of T sup 3 is equal to 480 degrees Celsius. Original temperature means the temperature is 480 degrees Celsius. Passing the steam through reheater at 12 bar. That means steam from 90 bar is expanded up to 12 bar, and when it reaches to 12 bar it is reheated again to 480 degrees Celsius. The expansion after reheating takes place. So after reheating again expansion of steam is carried out, and that expansion of steam is carried out up to the condenser pressure of 0.07 bar. So PB back pressure is 0.07 bar. Find the efficiency of reheat cycle. So Rankine efficiency has to be obtained and work output if flow of steam is 5 kg per second. So here the work output in terms of kilojoules per second, that is nothing but in kilowatt, is asked. Neglect the pressure loss in the system and assume expansion through turbines. Expansion through the turbines are isentropic. Do not neglect pump work. So here it is specifically mentioned that the pump work is not supposed to be neglected. So this data will plot on TS diagram and HS diagram, and we will have the layout of this problem. Then afterwards we will collect the data and we will start to solve this problem with a proper planning. So now let us see, this is the ES diagram of a given problem. So this is point 1 where steam enters into the turbine. So this point 6, say point 6, this point we call as 7, this point we call as 8. 6, 7, 8, 1. This is a constant pressure process or constant pressure line which is shown on TS diagram. So the steam which enters into the turbine at point 1 has got a pressure P1 is equal to 90 bar. So steam enters at 90 bar and temperature of steam at point T1 is equal to at point T3, and that temperature is given as 480 degrees Celsius. So steam enters at 480 degrees Celsius into the turbine and then it is expanded. So this expansion is stopped at point 2. That means when the pressure of steam reaches to the 12 bar, so this line is known as a constant pressure line of 12 bar. When it reaches to the constant pressure of 12 bar, that is the expansion is stopped, and from that point 2 again steam is reheated so that the temperature of steam reaches to 480 degrees Celsius. So original temperature is given. Temperature at point 1 is 480 degrees Celsius, and at point 3 also temperature is 480 degrees Celsius. Condition is at point 1 pressure is 90 bar and at point 3 pressure is 12 bar. So this is the difference between point 3 and point 1. So again from point 3 steam is expanded isentropically from point 4 to 3 to 4 unless it reaches to 7 bar. 0.07 bar pressure. When it reaches to 0.07 bar, then steam is condensed. When it becomes a liquid, then it is pumped with the help of a pump from PB back pressure to the boiler pressure, that is pressure P1. So it is supplied from condenser to the boiler, which is working at a pressure of P1, and condenser is working at pressure PB. So now one thing we can note down here, this steam is expanded from point 1 to 2. So the condition of steam at point 2 may be superheated, may be dry saturated, or may be wet. So that is to be decided whether the steam at point 2 is superheated, or it is dry saturated, or it is wet. Where this point 2 has to be marked, that is the question. So that we have to decide, that we will see while solving the problem. Same problem is represented on HS diagram, that is Mollier chart. So here in this Mollier chart, this curve is known as a temperature curve, constant temperature curve in superheated region. So this is the line which indicates 480 degrees Celsius in superheated region, and 90 bar pressure line intersects at point 1. So this is the point 1 where the steam is at temperature 480 and pressure of 90 bar. So this point 1 is located. From this point 1, so isentropic process is represented by vertical line. So vertical line is taken, and that vertical line, wherever it intersects with the 12 bar pressure line, so this is P1, this is P2, and this is PB. So wherever it intersect with pressure of 12 bar, so that expansion is stopped. Again steam is reheated to original temperature of 480 degrees Celsius. Again that steam is expanded till it reaches to 0.07 bar. So now one thing we can observe here, so where heat is supplied and where work is done. So heat supply starts from 0.6 to 7. So this amount of heat which is added from 6 to 7 is known as a sensible heat. It is known as a sensible heat from 0.6 to 7. So this amount of heat which is supplied is sensible heat, and from 0.6 7 to 8, this amount of heat which is supplied is known as latent heat of vaporization. 7 to 8 latent heat of vaporization is supplied, and from 0.8 onwards the amount of heat which is supplied is known as enthalpy of superheated steam. So from 0.8 to 1, superheat heating of steam takes place. So when steam enters into the turbine, it is at 0.1, having temperature of 480 degrees Celsius and 90 bar. So from 0.1 to 2, steam is expanded, means work is done by the steam. So this is first work done one. So H1 minus H2, enthalpy at 0.1 minus enthalpy at 0.2 gives us work done by turbine in first step. Then again steam is expanded from 0.3 to 4. So this is work done 2. So if we know enthalpy at 0.3 and enthalpy at 0.4, this difference between enthalpy gives us work done. So this is work done 1 and this is work done 2. So to find out net work done, total work done is WD1 plus WD2. So this is work produced by turbine, whereas work consumed by pump work is from 5 to 6. So pump is using this work produced. So this work can be calculated. So net work is nothing but summation of WD1 plus WD2 minus of pump work. This gives us work done. Then heat supplied. Heat supply starts from 0.6 to 7, 7 to 8, 8 to 1. So enthalpy at 0.1 minus enthalpy at 0.6 gives us heat supply. So heat supplied is known, work done is known. From that we can find out efficiency of this plant, as well as net work can be obtained, and if we multiply net work by mass of steam, that gives us power produced. So here work is produced in two locations, 1 to 2 and 3 to 4. So these are the two locations where work is produced, and this is the location where work is consumed by the pump. So similarly, This can be represented on HS diagram. So from HS diagram, 1 to 2 is work produced before reheating, and 3 to 4 is the work produced after reheating of the steam. So this is WD1 and this is WD2. So by knowing enthalpy at point 1 and enthalpy at point 2, WD1 can be obtained. By knowing enthalpy at point 3 and enthalpy at point 4, WD2 can be obtained. Now coming to the next thing, what is given in this problem and how to solve this problem with easy method that we see. So steam enters at 90 bar into the turbine, then that steam is having temperature of 480 degrees Celsius, then it is expanded up to 12 bar, and again it is reheated to original temperature, means temperature at point 1 is equal to temperature at point 3. Looking at this diagram, temperature at point 1 is equal to temperature at point 3. So T soup 1 is equal to T soup 3. Then the after reheating, steam is expanded up to 0.07 bar. So this is 0.07 bar. Steam is expanded up to 0.07 bar, and the mass flow rate of steam is 5 kg per second. So efficiency of a reheat cycle can be obtained. So this is asked in the question, and work output. So work output is asked in kilojoules per second. That is nothing but, or kilowatt. So that is power is asked. Now to find out efficiency of reheat cycle, so this is the ratio of net work done divided by heat supply. So to find out net work done is equal to turbine work minus of pump work. So first we must know turbine work, then we can find out pump work. So turbine work is done at two locations, WD1 plus WD2. WD1 is given by H1 minus H2. We can see here H1 minus H2 is WD1 and H3 minus H4 is WD2. So here work done at 1 plus work done at 2, this is turbine work. Then pump work is obtained between point 5 and 6. So here from point 5 to 6 pump work is obtained. So the condensate is supplied from a pressure of PB to the pressure of P1. So P1 minus of PB into specific volume of liquid, that is here pump work is equal to VSF into P1 minus PB into 100. So this 100 is convert this work done in kilojoules per kg. Then after this, to find out this turbine work, so we must know the value of H1. So to find out value of H1, the condition of steam at point 1 is superheated steam. So steam is superheated. To find out enthalpy of superheated steam, we have to use formula H1 is equal to HF1 plus HFG1 plus CPS, specific heat of steam, T soup 1 minus TS1. T soup 1 is given to us, that is 480 degrees Celsius. So this saturation temperature, then enthalpy of liquid, latent heat of vaporization, these are taken at a pressure of P is equal to 90 bar. So this is given in the problem. So these values have to be taken at pressure of 90 bar. Then after that we must know value of H2. So to find out the enthalpy at point 2, so assuming that here it is assuming that steam is wet at the end of first expansion, if this point 2 comes here, so then steam is wet. Now let us assume that steam is wet. Assuming steam is wet, we will find out dryness fraction. If dryness fraction obtained is equal to less than 1, if it is say for example 0.9, then our assumption is correct. If dryness fraction is 1, then also our assumption is not wrong, but exactly we can say steam is dry saturated. But if x is equal to greater than 1, maybe 1.1, 1.2, then steam is not dry saturated or wet, our assumption is wrong. So steam is superheated. At that time we have to find out, or we have to use some other formula to find out this enthalpy. So that formula is nothing but similar to this. Enthalpy of superheated steam is obtained by HF2 plus HFG2 and CPS T soup minus TS. So that is to be used. So we have to use this by assumption. First we will assume that as a wet, then it may be wet or dry saturated. If dryness fraction x2 value is more than 1, then we have to change this formula. So to find out H2, HF2 and HFG2 can be taken at pressure P2. So at pressure P2, HF2 and HFG2 can be obtained because pressure is known, but we don't know X2. So in order to find out X2, we have to equate entropy at point 1 is equal to entropy at point 2. So here the process 1 to 2 is constant entropy process. Entropy at point 1 is equal to entropy at point 2. So here we have to write equation S1 is equal to S2. So to find out entropy at point 1, so we have to write this equation SF1 plus SFG1 plus CPS natural log T soup minus T1, because at point 1 steam is superheated and at point 2 steam is wet. So here this formula will cancel. So here we write this as SF2 plus X2 SF. So our assumption is steam is wet. So everything on left hand side is known: SF1, SFG1, CPS net, T soup 1 and TS1 at pressure of 90 bar. Everything is known. And on right hand side, SF2 and SFG2 at 12 bar can be known, but unknown is only X2. So from this equation we can find out X2, and that value of X2 can be substituted in this equation. There we can get H2. So if X2 obtained here is less than 1 or equal to 1, then no problem. If it is greater than 1, then we have to change this equation. So left hand side will remain same, but right hand side whatever I have struck out will come into existence. So in which condition this will come into existence? If X2 value after calculation, if X2 is greater than 1, then we have to calculate once again temperature of superheated steam at point 2. To find out the temperature T soup, we have to use this original formula which I had written earlier. So the assumption is to be proved whether it is wrong or right. Then after that we must know enthalpy at point 3. So to know enthalpy at point 3, H3 is equal to HF3 plus HFG3 plus CPS T soup 3 minus TS3. So this is at pressure of P is equal to P2, that is 12 bar. So at 12 bar, HF3, HFG3 and TS3 can be taken from steam table. So at point 3 we can see at point 3 pressure is 12 bar. At point 2 and point 3 pressure is same, and temperature at point 3 and temperature at point 1 is same because it is given in the problem. So here this data is taken at 12 bar. So everything is known, directly we can find out H3. Now rest of the things is H4. H4 has to be calculated. So to find out H4, assuming that enthalpy, the steam at point 4 is wet again. What is the assumption? Steam is wet. So assuming steam is wet, at the end of expansion. So this formula is written. So HF4 and HFG4 can be taken at pressure of 0.07 bar, but we don't know value of X4. So again, to find out value of X4, so we have to find out the relation, or we have to equate entropy at point 3 is equal to entropy at point 4, because process 3-4 is isentropic process or constant entropy process. So entropy at point 3 is equal to entropy at point 4. We have to equate. So here entropy at point 3 is equal to entropy at point 4. Entropy at point 3 is calculated because the steam at point 3 is superheated steam. Therefore, the formula to find out entropy of superheated steam is SF3 plus SFG3 plus CPS natural log T sub divided by T3. This is at pressure of 12 bar. So left hand side is taken at 12 bar, and right hand side SF4 and SFG4 is taken at 0.07 bar. So this data is taken at 0.07 bar. Only unknown is going to be X4. So this x4 which we obtain will be substituted in this equation, and then we can find out h4. So after getting h4 we can find out turbine work. So VSF is taken from steam table. P1 is given, PB is given, pump work can be obtained. From pump work, knowing pump work, turbine work, net work output can be taken. And from net work output, the reheat cycle efficiency can be obtained. This is the outline of problem to solve this numerical. Now, there are three pressures which are given in this problem. So pressure of 90 bar, 12 bar and 0.07 bar. So this data is taken from steam table. The saturation temperature, specific volume of liquid, enthalpy of liquid, latent heat of vaporization, then entropy of liquid and entropy of vaporization. So that is taken from steam table. So at three pressures, 90 bar, 12 bar and 0.07 bar. Already I have explained how to extract this data from steam table. Now to simplify this problem, we have to start from where to start this problem is the question. So now already we have taken the layout of this problem. So very first we can find out enthalpy at point 1, because everything is known to us at 90 bar. So enthalpy at point 1 can be calculated. To find out enthalpy at point 2 we have to find out dryness fraction at point 2. So first we have to find out dryness fraction, then we can find out enthalpy at point 2. So coming here, so to find out enthalpy at point 1, enthalpy at point 1, that is H1 is equal to HF1 plus HFG1 plus CPS T sup 1 minus T saturation 1. So this is taken at pressure of 90 bar. Point 1 is having pressure of 90 bar. From steam table, if we see this 90 bar, HF1 is 1363.23. So this is at 90 bar, HF1 1363.23, 1363.23 is HF1, and HFG1 is taken from steam table as 1380.9, 1380.9 plus of 1380.9 plus of CPS, specific heat of steam at constant pressure, is 0.1 kilojoules per kg degree Kelvin. Temperature of superheated steam at point 1 is 480 degrees Celsius, which is given in the problem. So here temperature of superheated steam at point 1 is 480 degrees Celsius. Then temperature of saturation at 90 bar. So from steam table, T saturation is 303.4 degrees Celsius. So 303.4 degrees Celsius. On simplification, we get this as 480 minus 303.4 into 1 plus 1389 plus 1360. So this gives us 3140.99 kilojoules per kg. Enthalpy H1, no, enthalpy at point 1 is directly obtained. But to know enthalpy at point 2, H2, we have to write formula HF2 plus X2 HFG2 with the assumption. What is assumption? Assuming steam becomes wet. when steam is expanded from 90 bar to 12 bar, so this point does not come here, we assume that point comes here. So if our assumption is correct, then dryness fraction value x2 will be less than 1, and if our assumption is a bit wrong, so dryness fraction will be 1. So even if dryness fraction is 1, our assumption is not wrong. But if dryness fraction value x2 is above 1, then our assumption is wrong. Then we have to change this formula, and then we have to write another formula. So now here HF2 and HFG2 at 12 bar can be taken, but we don't know value of x2. So to find out value of x2, we have to equate entropy at point 1 is equal to entropy at point 2. So entropy at point 1, so this is at pressure of P is equal to 90 bar, and this is at pressure P is equal to 12 bar. So entropy at point 1 can be written as SF1 plus SFG1 plus CPS natural log T soup 1 divided by T saturation 1, because steam at point 1 is superheated. So we have to write equation of entropy for superheated steam, which is equal to SF2 plus of X2 SFG2. This is at 12 bar. Now what is our assumption? Steam is wet. It is not here, it is in the wet region. So this is our assumption. We have to prove that our assumption is correct or wrong. So now what is unknown is x2. X2 is not known. So once we get x2 from this equation, we can substitute in the above equation and we can find out enthalpy at point 2. So SF1, entropy at point 1, entropy of liquid at point 1 at 90 bar from steam table is 3.2857, 3.2857, 3.2857 plus of 3.2857, then SFG1 is 2.3915 at 90 bar pressure. So this data is taken at 90 bar pressure. So 2.3914, 2.3914, 2.914 plus of 2.3915, it is 15, plus of specific heat of steam is 2.1, natural log temperature of superheated steam is 480 degrees Celsius plus 273. So one important thing I want to highlight here is this temperature must be in degree Kelvin. So here both, if you substitute in degree Celsius or degree Kelvin, makes no difference. It can be in degree Celsius or degree Kelvin, but in this equation it is compulsory that the numerator and denominator must be in degree Kelvin. Saturation temperature is at point 1 as 303.4. We can see saturation temperature is 303.4. So 303.4 plus 273, closing this bracket, is equal to SF2 at 12 bar. At 12 bar SF2 is 2.2165. At 12 bar 2.2165, 2.2165 plus of x2 into SFG2 is 4.3067, 4.3067, 4.307. On simplification, we will get x2 value. So what will be the x2 value that we will calculate? Point 2857 plus 2.3915 15 plus 2.1 to natural log 480 plus 273 divided by 3.4 plus 273, then minus of 2.215 whole divided by 4.3067. This gives us 0.93. So that means the dryness fraction is less than 1, means steam at point 2 is wet. So this point which is represented in this diagram is wrong. This point must be in this wet region. So this process will be here. So this line will not become inclined. So this point will be somewhere here. And when we extend this point 1, point 2 will be inside this diagram. So knowing this dryness fraction at point 2, we can find out enthalpy at point 2. So enthalpy at point 2 can be calculated as H2 is equal to, so HF2 can be taken from steam table. So we are using this formula. H2 is equal to HF2 plus of X2 HFG2. So HF2 can be taken from steam table as at 12 bar 798.64, at 12 bar 798.64, 798.64 plus X2 is 0.933 into HFG2. HFG2 is 1986.19, 1986.19. So enthalpy at point 2 can be obtained here to 1986.19 plus of 798.64. This gives us enthalpy at point 2 as 2653.50 kilojoules per kg. Enthalpy at point 1 is known. Enthalpy at point 1 is known. Enthalpy at point 2 is known. Now we have to find out enthalpy at point 3. So in next, enthalpy at point 3, H3 is equal to HF3 plus HFG3 plus of CPS T soup 3 minus T saturation 3. So this data is at 12 bar. So from steam table we can get HF3, HFG3, CPS is constant, T sub 3 is known, TS3 is known to us at 12 bar. So we can directly find out HF3. So at HF3, at pressure of at point 3, pressure is 12 bar. So this is constant pressure line. So this constant pressure line means pressure at point 3 is 12 bar. So HF3 at 12 bar, at 12 bar is 798.64, 798.64 plus of HFG3. HFG3 is 1986.19, 1980.19 plus of CPS value is constant, that is 2.1 kilojoules per kg degree Kelvin. T sub temperature of steam at point 3 which is given as original temperature. Original temperature is 480 degrees Celsius, means temperature at point 3 is also 480 degrees Celsius, 480 degrees Celsius minus saturation temperature at point 3 corresponding to temperature 12 bar. Saturation temperature is 187.99, 187.99. So this gives us enthalpy at point 3. So by knowing enthalpy at point 3, 2.1 into 480 minus 187.99 plus 1986.19 plus 798.64. So this will be enthalpy at point 3 is 3398.05 kilojoules per kg. So enthalpy at point 3 is known. Now we have to find out enthalpy at point 4. So to find out enthalpy at point 4, our assumption is enthalpy at point 4, steam is assumed to be wet at point 4, HF4 plus of X4 into HF4. So this is at pressure of P is equal to 0.07 bar. So point 4 has got a pressure of 0.07 bar. So this data HF4 and HFG4 can be taken from steam table at 0.07 bar. But we don't know X4, so X4 has to be obtained. So this process 3 to 4 is assumed to be isentropic. So here for isentropic process we can write as S3 is equal to S4. So at point 3 pressure P is equal to 12 bar and S4 is at pressure of 0.07 bar. Condition of steam at point 3 is superheated. Condition of steam at point 4 is wet steam. So entropy of superheated steam at point 3 is given as SF3 plus of SFG3 plus specific heat CPS natural log T soup 3 divided by TS saturation 3, which is equal to entropy at point 4 for wet steam is SF4 plus of X4 into SFG4. So here SF3 can be taken from steam table at pressure of 12 bar and this data SF4 and SFG4 is taken at 0.07 bar. SF3 from steam table at a pressure of 12 bar pressure of 12 bar 2.2165 2.2165 plus of SFG3 at 12 bar is 4.3067 plus of CPS is 2.1 natural log T soup 480 degrees Celsius plus 273 divided by saturation temperature at 12 bar is 189.8 plus 273. So this all data is taken from steam table. Here we can see 12 bar. So SF3 is 2.2165, 2.2165, 2.2165. SFG is 4.3067, 4.3067. So that is taken from steam table. Again at a pressure of 0.07 bar. So at 0.07 bar, the data on left hand side is taken. 0.07 bar. SF is 0.5590, 0.5590 plus X4 which is unknown into 7.7180. So from this we can get X4 value. So this data is taken from steam table at 0.07 bar. This is 0.5590. Just remember this. So at 0.5590 at 0.07 bar, so SF is 0.5590 and SFG is 7.7. SFG is 7.7180. So on calculation we will get X4 value as 0.165 plus 4.07 plus 1 into natural log 480 plus 73 divided by 189.8. 189.70 0.55 point users 0.05, the dryness fraction at 0.4. So once we know dryness fraction at 0.4, we can find out H4. Enthalpy at 0.4 is equal to HF4 plus 4 HFG4. So HF4 can be taken at 0.007 bar. 0.07 bar. So that is 163.40. 163.40 plus of x2 value we obtained as 0.905 into HFG4 at pressure of 0.07 bar. So here 2409, 2409.2, 2409.2, 2409, 2409.2. So on calculation we get H4 is equal to 160.4 plus of 0.905 to 409 gives us enthalpy at 0.4 2343.72 kilojoules per kg. The enthalpy at 0.4 is known. Now enthalpy at 0.5 can be obtained from steam table. So H5 is equal to enthalpy at 0.5. H5 is equal to HF5 and that is from steam table at pressure of 0.07 bar is 163.40 because pressure is 0.07 bar. 163.40 kilojoules per kg. Now pump work we can find out. Pump work. The pump work is nothing but specific volume of water Vf into P1 minus Pb into 100. The specific volume at pressure of 0.07 bar, which is given in this steam table. Vf is equal to 0.001, 0.00100 into P1, pressure at 0.1 or higher pressure is 90 bar. So this is 90 minus lower pressure is 0.07 bar into 100. So this works out to be 0.001 into 90 minus 0.07 into 100, 8.993 kilojoules per kg of steel. So this is known. Enthalpy at 0.6, H6 is equal to enthalpy at 0.5 plus of pump work. Enthalpy at 0.6 is equal to enthalpy at 0.5 plus pump work. So enthalpy at 0.5 is known, that is 163.40 plus pump work is known plus 8.993. So enthalpy at 0.6 can be obtained plus of 164, 172.393 kilojoules per kg. Enthalpy at 0.6 is known. Now once we know enthalpy at 0.6, heat supplied can also be obtained. So now we will find out work done 1. Work done 1 is equal to H1, or first we will summarize the data which is obtained in this. Now on the next slide we will just summarize the data H1, H2, H3, H4, H5, H6 and pump work, and then we will calculate the things which we need. Now in next slide we will write down H1, 2, H3, H4, H5, H6 and pump work. So first we will find out H1. So what was H1 value? 3114.9, 3114.99 kilojoules per kg. Then we obtained H2 value. H2 value was 2653.5, 2653.5, 2653.5, 2653.5 kilojoules per kg. Then obtained H3 value. H3 value was 3398.05, 3398.05, 98.05, 0.05 kilojoules per kg. Then we obtained H4 value. For was we'll recalculate this. Plus 905 409.2 2343.7 2.7. H4 value is 2343.7 43.7 kilojoules per kg. Then H5 value we obtained as 163.4, 163.4 kilojoules per kg. Then we obtained H6 value as 172.39, 172.39 kilojoules per kg. We obtained pump work. Pump work was 8.993, 8.993 kilojoules per kg. So this is the information that we have collected. Now the work done, turbine work can be obtained here. So turbine work is done between 1 to 2 and 3 to 4. So turbine work 1 is H1 minus H2 plus turbine work 2 is H3 minus H4. H1 is 3114.99 minus H2 value is 2653.5 plus of H3 is 3398.05 minus H4 is 2343.7. So this will be turbine work 11.111499 minus 653.5 plus 3398.05 minus 2343.7. This turbine work 15.84 kilojoules per kg. So this is turbine work. Pump work is known. So net work produced is equal to turbine work minus pump work. Turbine work is 1515.84 minus pump work is 8.993. So this is net work is equal to 9. Net work is equal to 1506.85 kilojoules per kg. So this is net work done. Now heat supplied. Heat supplied is between 0.6 to 7 sensible heat, 7 to 8 latent heat, and 8 to N1 superheat. So enthalpy at 0.1 minus enthalpy at 0.6, H1 minus H6 gives us heat supplied. So H1 value is 3114.99 minus H6 value is 172.39. So here we get 3114.99 minus 172.39. So this is 2942.6 kilojoules per kg. The heat supplied we know. Now we know net work done, heat supplied. Then in this problem it is asked to find out the work done in kilojoules per second. So mass of steam is given. So here the work done is given in kilojoules per kg of steam, but he is asking us to find out the net work done in kilojoules per second. So on the next page we will solve net work done in kilojoules per second is obtained by net work in kilojoules per kg into mass of steam, which is given in kg per second. Kg gets cancelled, kilojoules per second is going to remain. Net work in kilojoules per kg just we calculated as 1506.85. 1506.85. 85. into mass of steam is given in the problem itself. The mass of steam is 5 kg per second, which is given in the problem. Into 5. Answer will be 306.85 into 5. So this will be 7534.25 kilojoules per second, or that is called as a or in kilowatt, or else this can be written as 7.54 megawatt. This is the work done. So Rankine efficiency or efficiency of reheat cycle is equal to net work done in kilojoules per kg divided by heat supplied kilojoules per kg. Net work done is 1506.85 and heat supplied we calculated as 2942.6 942.6 into 100. So this gives us 0.85 divided by 2942.6, 51.20%. Efficiency is 51.20%. So two things are asked: net work done in kilojoules per second or megawatt. Mass of steam is given, so this is one answer, or this can be taken as the answer, and this is another answer, efficiency of plant. So these are the two things which are asked in the problem. We can see here reheat cycle, efficiency of reheat cycle, and work output. So this is asked in this problem. Do not neglect the pump work. To find efficiency of reheat cycle and work output. So this is how we have simplified this problem using steam table. So now same problem can be solved using Mollier chart. So just I will highlight how to obtain the points, or how to obtain the values at Mollier chart, and the rest of the things will be same. So here there will be a constant pressure line of 90 bar where it intersects with the temperature line of 480 degrees Celsius. So this point of intersection is taken 1. So from point 1 vertical line is drawn so that this vertical line meets to the 12 bar line. So this point 2 is obtained. Corresponding to point 1 we can see here enthalpy H1, directly H1 can be taken. From point 2 enthalpy taken as H2. Then this process of reheating takes place from point 2 to 3. So along this 12 bar pressure line we have to move where it intersects again the temperature line of 480 degrees Celsius. That point is marked as point 3. Again from point 3 the vertical line is taken so that whenever it intersects to the constant pressure line of 0.07 bar, there it has to be stopped 0.4. So here we can find out corresponding to 0.4 H4, and corresponding to 0.3 we can get H3. So by knowing H1, H2, H3, H4, the rest of the things become very simple. So now we will see how to obtain these values from Mollier chart. So let us see here Mollier chart. So this green line is a pressure line of 100 bar. 100 bar. So this line intersects with this constant temperature line of 500 degrees Celsius, sorry, 480 degrees Celsius. 480 degrees Celsius at point 1. This point 1 is located. Corresponding to point 1, enthalpy is taken as H1. H1 is equal to 300, 3300. This will be 50. So just above it means 3355. 3355. So we can take this data. H1 equal to 3355 kilojoules per kg. So in previous case H1 value was 3114. So by graphical method we obtained it as 3355. Then H2 value we can obtain. Similarly, just taking the vertical projection from this point, so wherever it meets to the constant pressure line of 12 bar, so there we stop. This line is pressure line of 12 bar. Where it intersects to the 12 bar, there we mark point 2, and corresponding to point 2 we get here enthalpy H2 is equal to 2800. Enthalpy H2 is equal to 2800 kilojoules per kg. Then again H3 can be obtained. So how to obtain H3? So along this 12 bar line we move constant pressure line, and wherever it intersects with this line of temperature at point 3, so this point 3 is marked, and corresponding to point 3, so H3 is taken as 3450. It will be 80, 3480. So 3480 kilojoules per kg. Then directly from point 3 the vertical line is drawn, so that this vertical line meets with the pressure line of 0.07 bar. So here we can find 0.1 pressure line and 0.05 pressure line. So there is no line of 0.07, so approximately it is taken at the center. So wherever the center of these two lines, wherever it meets, that point is marked as 4 and corresponding to point 4. So enthalpy at point 4 can be taken as 2350 2350 2390 kilojoules per kg. The enthalpy at point 4 is taken as 2390. H4 is equal to 2390 kilojoules per kg. So this is how H1, H2, H3 can be, H3, H4 can be directly taken from Mollier chart, and this can be used, this data can be used in finding the efficiency, heat supplied, work done, everything that can be obtained. So this is the use of Mollier chart. So in previous case we used many things here to find out H1 was directly, to find out H2 we have done some exercise. So to find out H2 we have used so many equations, then we obtained H2 as 2653. So here we obtained H2 as 2800. So some values will differ, so depending on this quality of graph, so these values will differ. So H3 is equal to 3480. So one thing I want to highlight is, so this point 2 which we obtained, actually the dryness fraction was 0.9 something, so that was wet, but here it is showing dry saturated or just above it. That means this is the error of graph, so because of that we won't get accurate values. So this is how we obtained H3 as 3480. 3480. So it was 3398. 3480 was there. So 34 we can say 3400. So this is approximately similar values or same values we get. So H4 we obtained as 2390. So there how much we obtained H4? 4 was 2490, here 2434. 2490, 2434. Sorry, 2390. Little difference you will get here, but the accuracy will be less by using a graphical method. Accuracy will be less, but the process of getting data will be rapid than the steam table. In steam table we must remember certain formulae, we must remember certain processes to find out the values, but that can be avoided using Mollier chart. So once you know H1, H2, H3, H4, directly we can use these values of enthalpies in finding this work done, turbine work. H1, H2, H3, H4 is known, turbine work can be obtained, so pump work can be obtained, everything can be obtained very easily. So this is the use of Mollier chart, but always you must remember that the accuracy of results will be less if you use Mollier chart, but time saving will be